Hi, in this video, we want to take a look at survival analysis using Python. So survival analysis is where we're interested in how long it takes till a subject exits a system. So we could be talking about someone surviving cancer. We could be talking about someone surviving another disease. We could talk about someone graduating from college, or we could talk about someone like an object breaking. How long will it last? These are actually all examples of survival analysis. So the big idea here is with a collection of our population, we don't know the actual final number. It's censored. We call it censored data. So if I'm looking at survival times, how long does a patient with cancer survive? So here, with all the patients in the study, I record when they die. But all the ones who survive, by the end of the study, I just write down the amount of time that they've been in the study, and then I denote that their data is censored. That it's so in the data set we're going to look at in a moment, it's like 120 is the time, is the censor time. So what we would put down is it's like 120 or greater. I don't know exactly when they passed on. I don't know when they exited. So now we can do this also with graduation for college, because if I start tracking students on how long it takes them to graduate, all the ones who don't graduate by the time I'm done collecting my data are censored because I don't know when they actually finish, when they complete it. For items breaking, if I can write down how long it takes for a machine to break. If I'm dealing with multiple assembly lines out of machines, and then I can when I'm all done, collecting data and recording, this might be over several years, I go, hey, all of these ones never broke down. They never exited the system. So it's this duration of time or greater till they break down. And survival analysis is really powerful, really interesting, I think. All right, so let's go ahead and start using Python. All right, so I'm going to bring in matplotlib, use inline, then I'm going to get NumPy and get a specific part of matplotlib pyplot. Let's get stats, and let's get the URL lib for requesting the data. All right, now this next part is a special function written by the author of the textbook. All right, this special function is going to take the data that we give it. It's going to check the censored status, yes or no, and the time, and then it's going to create a plot. And the plot's going to look like this up here. I've already ran the code. You can see that it kind of steps down along the way. So along this axis is the time, and here's the survival probability. So here we can see this curve. As time goes on, the probability of surviving is only going down. And let's see, we can look and kind of see like where's our big drop is always interesting, and where is it kind of flat drop, and then it flattens out as it goes. So let's go ahead and build the special function. Now I want to go through and get our data. So what we're going to do here, I'm going to get the URL where the data is stored, but this isn't the complete URL for it. I'm going to be missing some stuff. I need to specify that it's the text file for 2, or the text file for 3, 13.2 or 13.3 from the Altman textbook. And then we're going to use this plus symbol to concatenate the 2 strings together. And then we're going to pass those using NumPy's gen from text function. So let's go ahead and do that. So here is for the first data set, second data set, and here is the base URL for both of them. Let's take a look. So we go URL 1. We can see that it is the whole URL. It is the base with file 1 concatenated on. URL 2, very similar. Now what we're going to do, we're going to pass the URLs to the URL open package, sorry, function, and this is going to grab the data. Well, in its raw format, Python's not going to be able to read it as is. So we need to pass it to another function, the numpy's gen from text function, and we need to specify that commas are delimiting the data. And so let's do that. Okay, so now let's take a look at what we got. All right, let's see. So here's our data. We can see that the first subject died at time 30, then 50, 50, 51, 66, 82, 92. Oh, so almost right. I almost said something wrong. No, I'll come back to it. Notice that one. So we got time 30, 50, 50, 51, 66, 82, 92, then a bunch of 120s. All right, what probably happened was that the study ended at time 120. And the people that were collecting the data just said, well, I'm done collecting data. I'm just going to write 120, and I'm going to denote that the subject did not die in this time span. And so the 1 indicates that they did not exit the system during the study. Now, if I look up here, you see I've got 0, 0, 0, 0 on a bunch of these. These indicate that the subject did exit the study. And if this is like a survival analysis for like a cancer drug or something like that, exiting means they died, unfortunately. Now, what's going on with this 50 and the 1? Well, what happened here was the subject left, and we don't know. We know that they reached 50 or better, but we don't know exactly what happened. Same thing with the 66. The subject reached time 66, left the study. We have no further information. We don't know when the subject passes on. All right, let's take a look at data set 2. All right, wow, someone passed on at 5. That's not good. So then somebody exited at 6. And then here we can see that 11, 11, 13, 24, down the line, that these subjects all survived, or sorry, they all died at these given times. And then the rest made it to 120 or better. Now, did they pass on at 120, 121, 122? We don't know. All right, so what we want to do, first and foremost, I want to make a picture of it. So we want to make the Kaplan-Meier curve. And remember, I'm using the special function that's defined up here. So this is the definition for the Kaplan-Meier function. All right, so this defines the P's, the R's, the T's, and SP's and SE's for the curve. This is all we need to define our curve. Now, let's go ahead and actually make the plot. And here we can see what's going on. All right, so as time goes on, we can see that the probability of survival decreases, goes on, because once someone dies, they're not coming back. So survival probability can only go downhill as we go along. Now, the main thing we want to see in this, or that we notice, is that the red and the blue have kind of a gap. They're not that close to each other. They're not crossing each other. So there's kind of a, anytime they don't cross, you're going to be, prone to saying that these are two different data sets. Okay? So here it's a little bit close. And so these are kind of close to each other, but they don't cross. So right now I'm leaning towards concluding that these are two different populations. So in a situation like this, maybe there'll be two populations that have different drug treatments for cancer. One group gets one drug, the other group gets the other. We want to know which drug is better. All right, so now what we want to do, we want to actually do the log rank hypothesis test to see, are these in fact two different survival times, or are these statistically the same? So we want to get the times from our data set, and we want to get the censoring. And then we're going to, failures means that's when they die. Do the same thing. Now we're using the horizontal stack function to put our data together. And now, okay, so what all of this is doing is this is just setting up the like a bunch of vectors that we can put data in a moment. So one thing we don't want to, so whenever we build a vector, we don't want to take a number, then append, and then append, and then append. We want, that takes a long time in memory. What we want to do, we want to create a vector and have all the slots already established, and then we put in what we want at each time. From a user point of view, it's equivalent, but for the computer, it's better to like set up all the spots that you need something for first, and then fill in the spots, than it is to make a spot, fill it, make a spot, fill it, make a spot, fill it, and down the line. All right, so now let's go ahead and let's fill this in. And this is just going through and getting all of, conducting all of the calculations we need for the hypothesis test. All right, so this is a non-parametric test. This is using the chi-square distribution to get our p-value. Remember, if I have a small p-value, I am prone to rejecting the null hypothesis. And we get that p-value by taking the test statistic and looking at the chi-square distribution. We have observed minus expected squared divided by the sum of our v's. All right, let's see what we get. So let's actually take a look. All right, so the bigger the value, the more prone I am to rejecting the null hypothesis. All right, 3.2, it's kind of like a maybe, maybe not. So now let's go ahead and get our p-value. So here we have 1 degree of freedom. So we've got 2 data sets. And so it's going to be number of data sets minus 1 is our degrees of freedom. So 2 minus 1 is 1. We have 1 degree of freedom. What we're going to do, we're going to get the area to the right of our chi-squared value, to the right of 3.2 underneath the curve for this particular chi-squared distribution. Let's see what we get. All right, 0.07. All right, so looking at this, I'm going to fail to reject the null hypothesis and I will fail to reject the null hypothesis. We conclude that there is no statistical difference between the 2 distributions. Okay, so let's think about this. You'll notice that these 2 curves never touch. And you know, there's a kind of a gap between the 2 here and here, down here, down here. So like the picture is leading me to go, hey, there's a difference, but the hypothesis test is saying, no, there isn't a difference. All right, well, why is that? Well, what is going on, if we look at the size of our data, I've got 21 observations and 28 observations in each of the data sets. All right, so what's going on is it looks like there's a difference, but I don't have enough data to make that conclusion. When we do hypothesis testing, everything is set up so that I am prone to going with the null hypothesis. So we fail to reject the null hypothesis. We're prone to going with the null. The null in this situation is that the 2 distributions are the same. Okay, well, because of the structure, it takes strong evidence for me to conclude that 2 distributions are different. Now, why the reason why we set up hypothesis testing in this way is because it's so mathematically coherent. So ultimately, hypothesis testing is based on math, and we have to do things the way that like math likes it, because it's the way math is. So even though it's like a borderline case, even though like 0.07 is close to 0.05, and the district and these curves do have a gap to them, I still conclude that there's no statistical difference between the 2 curves. I hope you've enjoyed this, and I hope you're staying safe. Goodbye.